Bismillahirrahmanirrahim. Today we shall talk about the system time response of the second order system. Uh, Typically, a second order control system, we consider the following transfer function, which is called the standard form of the second order system. It is represented by Gs is equal to omega n square divided by a square plus 2 zeta omega n plus omega n square. You can see that the order of the denominator polynomial is 2. That is why it is called a second order system. There are two parameters in this denominator polynomial which completely describe the dynamic behavior of the second order system. And this includes the zeta, which is called the damping ratio. And the second one is omega n, which is called the natural frequency. Zeta damping ratio means it can be defined as the decreasing of the amplitude of electrical or mechanical wave. It's called damping. Means the decreasing of the amplitude of an electrical or mechanical wave is called damping. For example, if we have the response of the system, let's suppose this is the response of the system, and it goes and then it oscillates and finally it comes to the final response or the steady state response. So you see that there is some damping in the system. You see the amplitude is reducing. The amplitude is reducing to a constant value, to a steady state value, and this is called the damping. If the amplitude will not reduce and it will oscillate above the steady state value, so you see that it is not a you see the system is an unstable system, so it has no damping. So this is called the damping. Since we said that the transfer function, the second order transfer function, which is again I will write over here, that the second order transfer function g of s will be equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. Since the polynomial in the denominator gives the poles, and here we see that the order of the polynomial is 2, so we will have 2 poles, and this will completely describe the system. We already know that we can write this in terms of the roots. So if we write this in terms of the roots, then we have the zeros. Remember that we already discussed this one, equal to 1 to m divided by the denominator polynomial can also be described in terms of the poles s minus pi. So we see that those value of s for which the gs For those values of s for which gs approach to infinity becomes infinity, we call that roots, we call it the poles. So so we say that the denominator polynomial uh, will give us the number of the poles. Also, we see that the zeta and omega n, we say that this completely describe the complete system, the second order system. Completely describe the dynamic behavior of the second order system. Let's see that. We consider some conditions and discuss this, that how this change the complete system. Let's say that in the previous expression, this one, in this expression, let me use this one. In this expression, let's say that zeta is equal to 0. So you see that if zeta is equal to 0, then let me write the denominator polynomial, which is what? S square plus 2 zeta omega n s plus omega n square. And let's say that we have the following condition. Let's say that zeta is equal to 0. We see that if zeta is equal to 0, then you have what? Ds will become equal to s square plus omega n square. And if you find the roots, then you will see that you will have two poles. One will become means that s will become equal to what? Plus minus j omega n. So these the s at plus j omega n and it s minus j omega n will give the poles. So when s become equal to this one, the denominator polynomial will become equal to 0, and when s is equal to 0, then g of s will be divided by 0, which will approach to infinity. So let's say that if zeta is equal to this one, then we have two poles. One pole will lie over here and another will lie over here, and this is called the S plane. Remember that actually we will do this in the next session, but this is called the complex plane. And we say that the system becomes stable, or the system is stable, when the poles lie in the left hand side of this axis. For example, this axis. So if the poles lie along this axis from the imaginary line, so we say that this is the stable system. And if the root crosses the imaginary axis and goes into the right hand side, we say that the system will become unstable. So our target will to design the system in such a way as the roots will lie in the left hand side plane. Also, the path traced by the roots should lie within the left hand side, and once it crosses the imaginary axis, this axis, then we say that the system is no more in the a stable system. So let us consider this one. In this case, you see that uh, the poles lie on the imaginary axis. So it is neither in the right hand side nor in the left hand side. So it is just on the boundary of the left and right hand side of the S plane. So in this case, we call it to be the marginally stable or the undamped case. If we find the response, so the response will be like this. See, margin is stable because it is giving you the bounded output, but it is oscillating, so it is not coming to a single steady state position. So we also call it the undamped case. Undamped Okay, you see there the amplitude is not reducing, so it is called the undamped case. The second case will be when zeta is equal to 1. You see in this equation, when zeta become equal to 1, so you are getting the real roots. How you see that? Let me. So in this case, when zeta is equal to 1, so you are getting the expression will become equal to, let me use this one. So d of s is equal to s square plus 2 zeta omega n plus omega n square. So let's say that zeta is equal to 1. So if zeta is equal to 1, then d of s will become equal to s square plus 2 omega n s plus omega n square. You can say that it will become equal to square. So this means that you have two roots at s is equal to minus omega n. So it is along the real axis. So if you go back to the s plane, so this is the imaginary axis. So this is the s plane. So this means that the two roots lie again at, this is one root and this is a second root. So I just show the two roots lie at the same point, and this is minus omega n, and this is along the real axis. This is along the real axis. Um, Similarly, I will come to the response later on. First, let me find all these. So, in conclusion, what happens? In conclusion, you have the S plane, and you have the remember the G of S, which is equal to omega n square divided by S square plus 2 zeta omega n s plus omega n square. Uh, number one is when zeta is equal to, in this case, zeta, red one is what is zeta is equal to 0. When zeta is equal to 0, this means that you have the two complex roots. You have the two complex roots. Number second one is when zeta is greater than 0 but less than 1, then you have the two symmetrical roots above and below the horizontal axis, real axis, and they lie in the left hand side. Similarly, when zeta is equal to 1, then you have the two roots that lie along the real axis. And if you have uh, the two roots when zeta is greater than 1, then you have the two roots that lie along the real axis at different locations. So you see that we have these four conditions. When we have the zeta is equal to 0, when zeta is greater than 0 but less than 1, then we have the complex roots in the left hand side. When zeta is equal to 1, then we have the two roots at the same location, and when zeta is greater than 1, then we have the two real roots, and they lie along the real axis. So what happens in the first case, when zeta is equal to 0, then we have the uh, then in that case we have the unbounded case like this. You see, this means that when zeta is equal to 0, this is the undamped case, so it is not, the amplitude is not reducing. As you move away from this axis, You see, from the imaginary axis, and you move away from the imaginary axis into the left hand side, then we are getting the damping. So suppose this is the what the final response. So in this case, what happens? Then you are getting the damping. Now you see that the amplitude is reducing, and then finally it comes to the steady state point. When zeta is equal to 1, then the green line, you see, when we have the two roots at the same location along the real axis and the left hand side of the complex plane, then it is called the critically damped case, and it is like this. So it is a smooth rise and then come to the steady state position. So you see there is no overshoot, and the rise is smooth, um, and finally it smoothly come into the steady state, which is the desirable um, system. Finally, the third one is called the over dam, and the fourth one is called the over dam case, when zeta is greater than 1. So when zeta is greater than 1, so it is called the over damped case. So we see that in this case there is no rise, there is no overshoot, but the rise time will take more time. The system delay is more in this case, because this is the over damped case. So see that the location of the poles, and also the zeta, the value of the zeta completely describe the system, where it is the undamped case, where it is the underdamped case, also the critically damped case, and the over damped case. So we will discuss this systems, this kind of the system, but remember that for the system stability, the pole should be in the left hand side. As long um, as the poles remain in the left hand side, so the system remains stable. But as the it moves from the left hand side into the right hand side, then we can now say that the system is stable. So uh, our target is to find the time response analysis, like this one. So if this is y of t, so this is t, so we are going to find the time response analysis, that how the system will affect when you will increase the zeta further, or if the zeta is slightly increasing from 0 to, and before reaching to 1, how the system will response will the system will uh, change, the response will change. So we are going to find the unit step, we are going to apply the unit step function at the input. So we have the system, and this is equal to g of s, and we already know that this is equal to the second order system, so it is s square plus 2 zeta omega n s plus omega n square. And here we are going to apply the unit step function, which is equal to 1 over s, and we are going to find y of s. So this we are going to find, and more specifically, we are going to find this one. Now, the advantage of finding this y of t is that for different kind of system is that if we do not know the general expression for y of t, then we have to re-evaluate the system again and again. We have to find poles and zeros again and again, and we have to solve the system again and again, which will become too much hectic if we are repeatedly doing the systems, repeatedly doing simplification for the different kind of the system. So if we know the value of the damping zeta, and if we know the natural frequency, then we can easily find that if zeta is in certain range, we can find that whether it is the over damped case, critical damped case, or under damped case, and we can use the general expression of the y of t. So using the general expression of y of t, and we can easily write the expressions, and we can plot this expression also using the computer, or you can also plot it if you know the theory and the uh, of the complex system. So let's say that 1 over s, which is the unit step function, the Laplace transform of the unit step function. So it is applied at the input, and g of s is the response of the system. So y of s will be equal to 1 over s multiplied by omega n square divided by s square plus 2 zeta omega n s plus omega n square. If you simplify this one by using completing the square method, using completing the square method, so you can see that y of s is equal to what? Is equal to 1 over s, and this will be equal to omega n square divided by s plus zeta omega n square minus omega n square root of zeta square minus 1 square. So simply you can see take the square of this one and then subtract from that one, so you will go back into the original function. So now we have what we have. You see, in the denominator we have a square minus b square, a square minus b square, which can be rewritten as a plus b multiplied by a minus b using this formula. So if we use this formula and we rewrite this one, then we can see that y of s will be equal to 1 over s multiplied by, this will be equal to omega n square divided by uh, s plus zeta omega n plus j omega n under root 1 minus zeta square. This is 1, and then this is multiplied with s plus zeta omega n minus j omega n 1 minus zeta square. So let's say that we have 3 poles. One pole is at s is equal to 0 over here. You can see this one pole is at s is equal to 0. One pole is at s is equal to minus zeta omega n minus j omega n, this one. And another pole is at minus zeta omega n plus j omega n. So let's say that we have 3 poles. So one is equal to, at s is equal to 0. You have one pole over here, and let's say that we have 2 other poles, p1 and p2, which is equal to minus zeta omega n plus minus j omega n square root of 1 minus zeta square. So we have this one, and we have to consider the 3 cases. So we are considering the over-damped case. We are considering the critically damped case. Means that we have to consider 3 when zeta is greater than 1, which is the over damping. When zeta is equal to 1, which means critically damping. And when zeta is less than 1 but greater than 0, so that is called the under damping. So we will consider these 3 cases, and we have 3 poles in our case. So y of s is equal to 1 over s, and then we have omega n square divided by S minus P1 and S minus P2. So we can rewrite this one. So number one, case number one, the over, sorry, over damping case, and zeta is greater than 1. Now we already know that y of S is equal to what? We have omega n square divided by S, and then we have the two other poles, S minus P1 and S minus P2. So we have to find y of t. We have to find y of t, means the time response of the output function. In so you see, directly we cannot find this one. So we have to use the partial fraction, and when you use the partial fraction, then you have y of S will be equal to K1 divided by S plus K2 divided by S minus P1 plus K3 divided by S minus P3. So this means that you have to use the partial fraction, and you have to find the values of K1, K2 and K3. So we see, if you find the value of K1, K2 and K3, then we can use the inverse Laplace transform, and then we can get y of t is equal to K1. 1 over S is the unit step function, and then we have K2 e raised to power E1t plus K3 e raised to power E3t. So this will be the output response. You can say, let's say this is equation number A. So this is the output response, and we are going to find the values of K1, K2 and K3, and we can easily use this one, because you see the roots, they are real. The roots are real in this case, are maybe complex also, but the roots are what is called, they are not same, they are not repeated, and you can use the first way to find the first method of partial fraction when you do not have the repeated roots. So you have to find K1. K1, you see, you can easily find K1 by multiplying all with S, and then let S is equal to 0. So you see, K2 will become equal to 0, K3 will also become equal to 0, and you will left only with K1. So in that case, what you will have K1 is equal to y of S multiplied by S, such that S is equal to 0. So if you will do this one, then K1 will be equal to omega n square, and then you will have S minus P1, S minus P2, such that S is equal to 0. And further simplification, if you put the value of S is equal to 0, if you will put the value of S is equal to 0, then you will get K1 divided is equal to omega n square divided by S minus P1 multiplied by minus P2. Uh, um, we also know that um, we also know in this expression, the previous one, you see that S minus P1 and S minus P2, actually this is, if we go back to the original function here, so this is what, this is this function, and again, if you go back to the original function, so this is equal to this one. See this one. So in this, if you easily place the value of S is equal to 0, so the first one will become equal to the second one will also become equal to 0, and you are left only with omega n square. And the numerator, you also have the omega n square, so both will cancel, and you will get only k equal to 1. So instead of this one, you can also use that one expressions, the simple ones, and you will left with K1 is equal to 1. Similarly, if you will solve this for K2, then for K2, you have to multiply with S minus P1 on both sides. So all will become equal to 0 except the K2. So in this case, you will get what? You will get K2 is equal to, let me change the color, black color, is this one and this. So for K2, y of s multiplied by s minus P1 such that s is equal to P1. When you simplify this one, then you will get K2 is equal to omega n square divided by P1 multiplied by P1 minus P2, which are poles, and we already know the values of P1 and P2. Similarly, K2 will become equal to, you can multiply the numerator and denominator with what? With P2. So let's say this is P2 and this is P2. Why? Because we know that P1 and P2 is equal to, if you multiply both these, so from this you will get omega n square. So if you get this from this omega n square, then you can erase uh, this one with this one. And you are left only with K2 is equal to P2 divided by P1, no, divided by P1 minus P2. So this is the value of K2, and when you solve this for K3 again, then you will get what? Then you will get K3 is equal to P1 divided by, using the same method, you will get this one. So we can use the value of K1, K2, and K3 in equation number A over here, in equation A. And then we can rewrite this equation, and we will get our solution. So y of t will become equal to 1 plus K1 is P2 divided by, sorry, P2 divided by P1 minus P2, yes, e raised to power P1 of t plus K3 is P1 divided by P2 minus P1 e raised to power P2 of t. So we are getting this expression, and you can now easily see that if P2 is greater than P1, if it is a greater, means a larger value. So this is the general expression, y of t. This is the general expression, and let's say this is equation B. So we'll use this expression also. But if you know that the value of P2 is greater than P1, then what will happen? See, if magnitude of P2 is greater than P1, so in this case, what will happen? You see that this one, the you see this P2 divided by this one, so this one will become equal to what? So P1 is very small value. If P1 is very small value, then P2, and this will be nearly equal to P2. So this will be approximately equal to 1. And if P2 is a very large value in this case, so anything divided by a very large value, so this will become equal to approximately equal to 0. Approximately equal to 0. So you are left with what? You are left with so you will left with y of t is equal to 1 minus e raised to power P1 t. So you are left with this one. So this is the case when the two poles are away from each other. So this means the P2 is a larger value compared to P1. So the gap between the two is a very large value. You can say 8 times, 10 times. So even if 10 times, so 1 divided by 10, so it will become equal to 0.1. So this is approximately equal to 0. So this is not the closed form. The closed form is the expression B. So and finally you can use the value of P1. We already know what is the value of P1. So the value of P1 you can find from the poles over here. When we when we have the sorry, over here somewhere. This one. Also, you can see that in this case, if okay, later on we can explain this one. So let us consider this one example. Let's say that we have what exercise. Let's say that g of s is equal to 9 divided by s square plus 9s plus 9. We are going to find the unit step function. Consider unit step function which is applied at the input of the system. So we are going to find y of t, the time response analysis. We are going to find this one, and we are going to apply the unit step function. So it is straightforward. So if you will apply the unit step function at the input, so y of s will become equal to 1 over s multiplied by 9 divided by s square plus 9s plus 9. Now one method is to simplify this one, and you will go into the same things which we already derived. So which is a lengthy process. The another thing is to use the closed form expression for y at t that we already derived. So if we use this one, we can get our solution. But we have to compare this with what? We have to compare this expression with s square plus 2 zeta omega n s plus omega n square to find the value of zeta and the natural frequency. So we have to find the value of zeta and natural frequency. So it's straightforward. Omega n square is equal to 9. Omega n square is equal to 9. So from this we find that omega n is equal to 3. So this is found. And if you find 2 zeta omega n is equal to 9, so omega n is equal to 3, and then you can find zeta is equal to 9 by 6, which is equal to 1.5. So we also find the value of zeta, and you see that the value of zeta is greater than 1, and when it is greater than 1, then it means that this is the Bourdain case. So you can find your findings over here. You can find this one, the equation B. You can easily find this one. So you can use this expression, and you can find the solution. So the question is, what is P1 and P2? Because here we have P1 and P2. So P1 and P2 we can find from the this expression, this one. So P1, you see, we know the zeta, we know omega n, and then we can simplify this one. So we will get our P1 and P2. So if you will use this expression for P1 and P2, and use the values of zeta and omega n, which we derived over here, so we see that P1 is equal to minus zeta omega n plus omega n, and then we have zeta square minus 1. So this will be equal to P1 will be equal to minus 1.1459, and similarly P2 will be equal to minus zeta omega n minus omega n square root of zeta square minus 1. So P2 will be equal to minus 7.8541. It's straightforward. Magnitude of P2 is greater than P1, so we can use the another solution also. But if you use the closed form solution, equation B, then you will see that K1 is equal to 1, K2, which is equal to what? Is equal to P2 divided by P1 minus P2. And finally, we have K3, which is equal to P1 divided by P2 minus P1. So you can find the value of K1, K2, and K3. So K1 will be is already equal to 1, K2 is equal to 1.171, and K3 is equal to 0.171. And the rest is the solution, which is y of t, which is equal to 1 plus 0.171 e to power minus 7. You see P2 P2t, so P2 is equal to 7.85 t minus 1.171 e to power P1t, and P1 is equal to minus 1.146 multiplied by t. So you got this expression, uh, and it was pretty easy if you will use uh, the closed form solution. So similarly, you can find for the other function also, if other second order function also, if you know the equation B, and if you know, especially if you know the value of zeta, which should be greater than 1, should be greater than 1. So let's say that g of s is equal to what? G of s is equal to the same case 9 divided by s square plus 6 zeta s plus 9. And let's say that zeta is increasing, means in previous case we have zeta is equal to 1.5, so we can say zeta is equal to 2, 3, 4, and so on. So if zeta is increasing, let's see that what is the response of the unit step response of the this system. So this is the YRT, and this is T. Unit step response means the input is the unit step function. So the input is unit step function. So let me use this one. So this is the input. This is the input. So this means that the force response or the final response should be the unit step function. It should be equal to 1. Now what is y of t? Y of t should be, now let us plot y of t for different values. They say that uh, if zeta is equal to 1.5, and if you use the same expression as this one, which we developed earlier, this one, you see this one. So if you use this expression and you plot this one, so what you will get? You will get this one. So you will get this expression. So this is for zeta is equal to 1.5. Let's say this is equal to 1.5. Now please check that if you will increase the value of zeta, let's say that zeta is equal to 2, so the damping will increase. See, damping will increase. If you further increase the zeta is equal to 4, so the system will become overdam. So you see that this is why it is called the overdam case. When zeta is greater than 1, as you will increase zeta, the overdamping will increase. So it will come toward this side. So the overdamping will increase, and you are getting the final response. Overdamping is increased means that the rise time will increase. See, the rise time will increase. Also, the settling time will increase. So initially, if this is the settling time in the first case, if this is the settling time, then in the second case, this is the settling time. See, this is the TS. In the third case, this is the settling time. So you see that Ts increases. So in the first case, Ts is this one. And as the damping is increased, so the settling time will increase. So we have to know this one also. Uh, Now let us consider the critically damped case. Critical damped case, we have zeta is equal to 1. So in the critically damped case, zeta is equal to 1. And what will happen to the transfer function? So which is equal to omega n square divided by s square plus, we have 2 zeta omega n square. So zeta become equal to 1, and then you will get what? 2 omega n s plus omega n square. It is straightforward. Straightforward because you have see the two roots are at the same location, means that um, y of s, which is equal to x of s multiplied by g of s, the output response of the system when the unit step function is applied, and the we know that the x of t is equal to the unit step function, then x of s will be equal to 1 over s. So y of s will become equal to omega n square divided by s, and this will become equal to s plus omega n square, which is straightforward. So again, you see that you have the repeated roots over here. So over here, see, we have the repeated roots over here. So in the denominator, if you have the repeated roots, so we will use the second method of the partial fraction by finding the repeated roots c1 and c2. We already know this one. So this means that the this one omega n square divided by s plus s multiplied by s plus omega n square will be equal to what? This will be k1 divided by s plus, you can say c1 divided by s plus omega n square, and then we have c2 divided by s plus omega n. So we have to find C1 and C2 for the repeated roots and K1 for the real root. So let us use the partial fraction method and find the value of the K1 and the C1 and C2. So K1 is straightforward, so you have to multiply this by S. So you see that at both sides S will cancel, and here you will have omega n square divided by s plus omega n square, and then you have to place s is equal to 0. So C1 and C2 will cancel out, and you will left only with omega n square divided by omega n square. Means that you will get what? Omega n square, sorry, omega n square divided by s plus omega n square, such that s is equal to 0. You will get this one finally. And when you place s is equal to 0, so you will get k1 is equal to 1. To find k2, c1, you can say c1 is equal to what? Multiply both sides with the root, the you see the denominator, this one, s plus omega n square. So you will get what? S plus omega n square multiplied by omega n square divided by s multiplied by s plus omega n square, and then you have to place s is equal to minus omega n. So all will become equal to 0 except c1. So c1 in this case, this will cancel out, and you are getting c1 is equal to omega n square divided by minus omega n, so you will get minus omega n. And similarly, you can also find C2, but C2 you have to find by taking the differentiation of K1. So means that dy ds what? S plus omega n square multiply by omega n square divided by s into s plus omega n square. And then again s is equal to minus omega n. So this is again the same thing. So if you simplify, s is equal to minus omega n, you have to place this one. This is equal to minus omega n. So from this you will get C2 is equal to minus 1. Simplify this one and you will get C2 is equal to minus 1. So you have to take the inverse Laplace transform of this function. You see that if you will take the inverse Laplace transform of this function, you have the unit step function over here, and then 1 over s square will be equal to what? Is equal to t. And then we have a delay, so it will be represented with the exponential function. And of course, we have 1 over s with the frequency shifting, so which will be represented with the exponential function. So finally, you will get what? You will get y of t is equal to 1 minus omega nt, and then we have the exponential function e to power minus omega n t, and then we have minus 1, and then we e to power minus omega n t. So generally you will find y of t is equal to what? 1 minus 1 plus omega nt multiplied by e raised to power minus omega n t. So this is our expression A for the critically damped case when zeta is equal to 1. So we can directly use this expression for the unit step function when applied at the input, so we can find the y. For example, consider the this example when we have g s which is equal to what? 9 divided by s square plus 6s plus 9, and x of t is applied at the input. So we are going to find y of t. So we will compare g of s with the standard form of the second order system. So we will compare with omega n square divided by s square plus 2 zeta omega n s plus omega n square. So if you compare with this one, then you can see that omega n is equal to square is equal to 9, or you can say that omega n is equal to 3, and 2 zeta omega n will be equal to 6. So omega n is equal to 3, so this means that z is equal to 6 by 6, which is equal to 1. Since zeta is equal to 1, this means that we have the two poles at the same location, and we have the critically damped case. So in the critically damped case, we have to use this expression, equation A, and we have to find the solution. So solution is straightforward: 1 minus 1 plus omega n, we already know 3t, and then we have e raised to power minus 3. So you see that it was that much easy if we know the general expression for the over-damped case as well as the critically damped case. So in this case, it will become equal to y of t is equal to, using the equation A. So this will become equal to 1 minus 3t e raised to power minus 3t, and then e raised to power minus 3t. So you get this expression. You can also draw this one. So if you will draw this one, so you will get this smooth curve. Let's say that this is the input function, which is the unit step function. So this is equal to 1. And then if you will find the output, so you see that you will get the function, and then a smooth curve over here, and finally you will get this to become equal to the unit step function. So if you compare this with the over-damped case, for example, this one was the over-damped case. You see, for some z value, for z, you can say is equal to 4. So here, the red one is for z is equal to, the red one is for zeta is equal to 1. So you see that the rise time that improves. You see the rise time will become minimum. The settling time is also improved. So this is the settling time. So this is settling time, You see, which improves compared to the this one, where the settling time is more over this one. So you are improving the settling time. Also the response of the system, if you properly design the system, and you are getting the two poles at the same location. Overall, the system is stable. It will not cross the unity line, which is the input, this line. It will not cross this line. But you see that the rise time, the settling time, the delay time all depends on the value of this depends on the value of what is called zeta, and the natural frequency. Let us consider the third case. In the third case is when we have zeta is less than 1 but not equal to 0, because we know that when it is equal to 0, then the poles will lie on the complex, what is called the imaginary axis, and then it is undamped, or you can say that the marginally stable system, which is not the stable system. So that is why the zeta should be greater than 0, so that the poles will lie in the left hand side, so the third case is the under damped case. Means that zeta is less than 1 or this is greater than 0. Remember this one. So let's say that we have again, we'll go back to the from where we started. We have the we are going to apply the we have the g of s, which is the second order system, and then 1 over s is applied at the input, means the unit step function is applied at the input. We are going to find y of s. In general, we are going to find y of t. So we know what is y of s. We know that y of s is equal to omega n square divided by s multiplied by the transfer function 2 zeta omega n s plus omega n square. So we have this one. We can rewrite this expression. We can rewrite in this way, that y of s is equal to 1 over s minus s plus 2 zeta omega n divided by s square plus 2 zeta omega n s plus omega n square. It's straightforward. You can say that you see, if you will simplify this again, you can get the original function. You see this you see, let me show. You see, if you take this as the LCM, you see s multiplied by s square plus 2 zeta omega n s plus omega n square, then this one will become equal to s square plus 2 zeta omega n s plus plus omega n square, and the second one will become equal to minus a square minus 2 zeta omega n s, this one. And then you can see that you can cut this with this one, cross this with this one, and finally you are left with omega n square divided by this one, which is the original function over here. So we can use this expression, y of s is equal to 1 over s minus this one. So we can use this expression. Further, we can also say that 2 zeta omega n is also equal to zeta omega n plus zeta omega n. So we can also write like this one. And if we write like this one and find the roots of the denominator polynomial, which we already know, from the previous what is called word end case. So if we'll use this one, then remember that we will get what? Then 1 over y of s will become equal to 1 over s minus s plus zeta omega n divided by this will become equal to s plus zeta omega n square plus omega n, and then we have 1 minus zeta square, 1 minus zeta square. So if you find the square of this one and square of this one, and then you simplify, so you will get the original function. Minus zeta omega n divided by, again, s plus zeta omega n square plus omega n, and then we have 1 minus zeta square whole square. This is straightforward, the denominator polynomial, this one. This is straightforward. How you see that this will become equal to s square plus 2 zeta omega n s plus zeta square omega n square, and then this one will become equal to plus this one will become equal to omega n square multiplied by this one. So omega n square minus omega n square zeta square. So we can say that you can cross this one with this one, um, and then you are left with what? S square plus 2 zeta omega n s plus omega n square. So you are left with s square plus 2 zeta omega n s plus omega n square. So it was straightforward. So you have y of s which is equal to this one. Remember that y of s is equal to this one. So we'll use this one now. Um, we'll use this one, and we have to find the solution. Remember that we know that if you find the inverse Laplace transform of this one, so this one is easy. You see, this one will be equal to what? This will become equal to unit step function. And then we have this function and this function. So let us separately find the inverse Laplace transform of these. So if you separately find the inverse Laplace of this, we know that the inverse Laplace transform of s plus a divided by s plus a square plus omega square. What is the inverse Laplace transform of this one? This is equal to what? Cos omega t, and then we have the delay e raised to power minus at. Similarly, we know that the inverse Laplace transform of omega divided by s plus a square plus omega square, this is equal to what? This sine omega t, and then we have e raised to power minus at. So we'll use these two functions to find the inverse Laplace transform of what? This function, this one, and this one. So the first one is, you see, s plus delay. So this will be the cos function, and the second one is the omega n. So this will be the sine function. But we have this what is called omega n, and then we have square root of this one. So we have to find this by proper way. So by using the proper way. So the first one is straightforward. So it is the delay, which is equal to e raised to power minus zeta omega n, which is the delay, and then we have the cos the cos function. So the first one will become equal to what? Laplace transform of s plus zeta omega n divided by s plus zeta omega n square plus omega n square root of 1 minus zeta square, and this is square. So this will be equal to this will become equal to what? This will become equal to cos what? Omega n t square root of 1 minus zeta square, and then multiply with the delay, and delay is equal to e raised to power minus zeta omega n, e raised to power minus zeta omega n. So this is the first one. The second one will become equal to the Laplace transform of what? We have omega n, and then we have 1 minus zeta square divided by s plus zeta omega n square, and then we have omega n square root of 1 minus zeta square whole square. So this is the sine function. Omega divided by s plus omega, a square plus omega square. Remember that one. So this one will become equal to what? The delay e raised to power minus zeta omega nt. And then we have the sine function, sine omega n t multiplied by 1 minus zeta square. So the inverse Laplace transform of the original function, which is this one, this function will become equal to unit step function. Then we have the cos function, and then we have the sine function. So and do some simply multiplication also in the numerator and denominator, because we have to make it suitable for the inverse Laplace transform. So finally, what you will get? You will get y rt will be equal to 1 minus. Then we have uh, the cos function with the exponential e raised to power minus zeta omega nt, and then we have the cos omega nt multiplied by 1 minus zeta square, and then we have the delay function. Sorry, this is minus zeta omega nt. So delay function, and then this will be multiplied with the sine omega nt multiplied by 1 minus zeta square, and also this will be divided by 1 over square root of 1 minus zeta square over here. You see, we use this one over here, and then we have the zeta already in the numerator. So zeta is already in the numerator. So what we did, we multiply this one and divide this by 1 minus zeta square. So like this one. So we multiply and divide by 1 minus zeta square, and here we divide. So this will be equal to square root of 1 minus zeta square. So this will become equal to zeta divided by 1 minus zeta square. So this will be taken as common. So if you take this one as common, so this means that this will be equal to zeta divided by 1 minus zeta square root, and then you can use the negative sign over here. So this is the closed form solution which we get over here. If you further simplify this one, so you can also do that one by, you see, by taking the sine term as constant and using the formula, by using the formula cos alpha minus beta, which is equal to cos alpha cos beta plus sine alpha sine beta. So you can also use that formula, and you can further simplify this one, and you can use this as the general expression for the word end. For example, if you simplify this one using cos alpha minus beta, which is equal to cos alpha cos beta plus sin alpha sin beta, then equation A can also be written as y of t, which is equal to 1 minus 1 over square root of 1 minus zeta square, and then we have the delay e raised to power minus zeta omega nt, and finally you will get what? Cos function cos of something, and that something, let's say that this one, that something will become equal to what? Is equal to omega n t square root of 1 minus zeta square minus tangent inverse of what? Zeta divided by square root of 1 minus zeta square. This is equal to this one. So you can also use the second expression. Consider the let us consider an example. Example is, let's say that g of s is equal to 9 divided by a square plus 3s plus 9. So straightforward, if you compare this with g of s is equal to omega n square divided by a square plus 2 zeta omega n s plus omega n square, then you can see that omega n is equal to 3. And if you find zeta, so zeta omega n is equal to what? Is equal to 3. This means that zeta is equal to 1 over 2, which is equal to 0.5. So in this case, zeta is less than 1. So this means that this is the underdamped case. In the underdamped case, we are going to use the expression for the y of t when the unit step function is applied at the input. So we can use this expression or the second expression, which is the b. So let us use the second expression. In the second expression, we have tangent inverse zeta divided by 1 minus zeta square. So we have to find that one. Tangent inverse of what? Zeta divided by 1 minus zeta square. So if you find this one, this is equal to 30 degrees because zeta is equal to 0.5. And similarly, you have to use the other term omega n multiply omega n is equal to 3 and 1 minus zeta square. Zeta is equal to 0.5. So if you simplify this one, so it will become equal to 2.598. So finally, what you will get? You will get y of t will be equal to 1 minus 1.155 e raised to power minus 1.5 t, and then we have cos of what? 2.59 t minus 30 degrees. So you can get this one. Now let us do some kind of the observation from the overdamped case that what will actually happen. What will happen? We can have three kind of the cases for the overdamped cases. For the overdamped cases, uh, number one is before going into that detail, if we find the unit step response just like the other cases. So this is the unit step, and then we have the different kind of the responses. So let's say that this is equal to what? This is equal to zeta, and as zeta will increase, so you see that the system will go from the overshoot will also increase. The stability will somehow you see reduced. How you see that? Let's say that this is zeta is equal to 0. You said zeta is equal to 0.9. So this is 0.9. Because why? Because we already know that this is the critical case when zeta is equal to 1. So this is equal to zeta is equal to 1. So this is zeta is equal to 1. So as you go from zeta is equal to 1 into this side, into this side, the overshoot will increase. So this is zeta is equal to 0.9, the red line. If you will make zeta is equal to 0.5, so this will become like this. You see the overshoot increases, and then later on the settling time will also increase. So the overshoot is increasing, the settling time will also increase. If zeta become equal to 0.1, said this one, zeta is equal to 0.2. So let's make it 0.2. So what will happen? So further it will increase. So this will become like this. So you see later on it will become like this table. And if you make zeta is equal to 0, so if zeta is equal to 0, then it is the undamped case, and it will not return to the steady state position. So it will oscillate about the the final steady state position. So you can easily see that when zeta is equal to 1, so it is the critical case. We have the very smooth rise over here. When zeta is decreasing, zeta is less than 1. So when it is decreasing, so the overshoot is increasing. The rise time, you see the rise time is also decreasing, but the overshoot is also what is called increasing. So which is critical. So you see we have to control the overshoot. We do not want this the response to cross this line. You see this line. So we have to balance the system in such a way as to reduce this one. So we have to keep this overshoot, we have to bring it to the other side. You see we have to bring it to this side. We have to reduce this one. So this means that we can increase, we can do this one by increasing the damping, but if we increase damping to a higher value, you see to this value, so what will happen? So the rise time will, so the system response will become slow. In simple word, the simple response will become slow. So this means that it requires proper designing to find the position, the response, the system poles, which give you the a very smooth rise, like the critical case over here. So smooth rise, and you see it steadily comes into the final steady state position. So smoothly come into the final steady state position. Uh, in conclusion, if zeta is equal to 0, so there is no return to the steady state position. If zeta is less than 1, and then it depends on the value of zeta. If it is near to 1, so you see the overshoot will be less. And if it is away from 1, then there will be maximum overshoot. If zeta is equal to 1, then this is the critical case. The two poles will lie on the same point, and the system will smoothly come into the steady state position and nicely rise. If zeta is increased from 1, and further if you will increase, the system response will become slow. So that was the conclusion. And one thing more, let us explain also this one, that what will happen if we have the different in the what is called the underdamped case. We can have also some other kind of the responses. For example, they say that, see, this is the what is called the S plane. And then we say that these are the poles. So which case is this one? Is straightforward. This is the case when we have the this is the underdamped case. This is the underdamped case. So in this case, if we'll plot the response of the system, in this case, let's say the unit step response. So this is the final steady state position. So in this case, what will happen? So the system will rise, and then it will come to this point. Now let's see that what will happen if the imaginary axis is changed, not the horizontal axis. So it means that if the poles move along this side, if you move the poles along this side, the overshoot will increase. Remember that the overshoot will increase. It will increase like this. If you further move the poles along this side, you see at this side, so it will further increase. So the overshoot will increase. Um, See, if you will move the poles along this side, remember that the poles will be symmetrical. This line will be symmetrical in the S plane. The both poles will be symmetrical above and below the real axis. So it will be symmetrical. So this is the pole motion. So if the real axis is fixed and the horizontal axis is what is called variable, so if you will increase the horizontal vertical axis, so the overshoot will increase. So remember that one. The second thing is what will happen if the pole move along the horizontal axis. Means that same plot. So what will happen if we have this one? So these are the poles. Sorry, the red one. Let's say these are the poles. So in this case is straightforward. So we have the unit step response over here, the final response. So in this case, what will happen? The if you will this is the first response. So this is the first response. And if you will move this along the axis, for example, this one, if you move along this motion, which means that the vertical position is fixed, but the horizontal position is changed. Remember, as the poles will move along the real axis, and away from the imaginary axis, so the system stability increases. So in this case, what will happen? The overshoot will the system stability will increase. So in this case, the system stability will increase. Remember, they will have the same frequencies. I think I didn't plot properly, but they will have the same frequencies, but the overshoot will reduce. And if you further move this one, so this will further reduce. So this will further reduce. But let me first plot this one properly because I didn't plot properly. So this one, and if you further move this one toward this side, so what will happen? So this will further reduce. Maybe this one. So you see you can reduce the overshoot if you will change the real part of the complex planes. And finally, what will happen if we have the constant damping ratio? Means that if we have this, we have this. Sorry, this one is red again. So this is red S plane. So if you will plot this one, the unit step response. So in this case, if this is the response, I just make the response like this for the comparison. And then you are moving the poles along this side. Sorry, this one means the along this where the ratio is same. Where the ratio is same. So if you move like this, so what will happen? So they will have the same overshoot. The overshoot will remain the same, but one thing will change, and that is, you see, that one thing is you can clearly see that what is that one thing, and that is the rise time. So in this case, the rise time will reduce. So we have these three cases. So in the under dam case, so in the first case, you see that the imaginary axis is changing. The second one, the horizontal axis is changing, moving away from the imaginary axis. And the third one is the constant damping ratio. So in that case, the rise time will reduce. They will have the same overshoot. In the first case, if you will increase the imaginary axis, the vertical axis, so the overshoot will increase. And the second case, if you will increase the real axis, so this means you will reduce the overshoot, and they will have the same frequencies. Finally, we have the time response specification, and in this case, we have the in the time response we have the rise time. The derivation is already given in the note, so you can read that one also. But the rise time is equal to omega d tangent inverse of omega d divided by minus psi, where this omega d uh, is equal to what? This is equal to omega n square root of 1 minus zeta square, and psi rho is equal to zeta omega n. So this is the rise time. The derivation is already given in the note, so you can read that one. Rise time is means that when the system response rises from 10% to the 90%, 10% to the 90%. The second one is the peak time. So peak time is when you get the first peak. You see the maximum peak, so that is called the peak time. So mathematically it is equal to pi divided by omega n divided by 1 minus zeta square. And then we have the maximum overshoot. So let me explain over here. So this is the unit step function, and then we have the response of the system with this one. So rise time is what? When the final response from 10% to 90%. So this is the rise time. Uh, Peak time is equal to what? Peak time is when you are getting the first peak over here, the maximum overshoot over here. So that is called the peak time, TP, of the under dam case. In the other two cases, there is no peak time because in the critically dam case and the over dam case, there is no peak time because the rise is slow. The third thing is the maximum peak, which is this point. You see this point minus this point, which is MP. So MP is actually the response T when equal to the peak time at this point minus response when T is approaching to infinity, means the delay. Sorry, this one, the steady state point. And if you are going to find the percentage of this one, then you can also divide this by y going to infinity multiply by 100. Multiply by 100. So this whole function multiply by 100. So it will give you the percent overshoot. And the third one is the settling time. So we already know about the settling time. So settling time is what? Is this one when you are getting the forced response. This is the settling time, TS. And we already know that settling time is equal to what? The settling time is equal to 4 time constant. In this case, in the second order system, the settling time will become equal to 4 divided by zeta omega n. So this is all for today's class. Next time we will see that what will happen if what are the other ways to find the stability of the system. Means that we have to find the stability of the system, and we can also study the response of the system using the root locus technique. So once you study the root locus technique, then you will be able to properly design the system. So we will try to understand what are the root locus, how the poles behave, how they move, and how we can make the system balance, and how we can design the system. So that is it for today's class. I hope that will be useful for you. If you have any question, you can contact me, and you can also post a question in the group. Thank you very much. See you next time. Allah Hafiz.